Well, good afternoon to all of you. We have experienced some problems with the connection, so we have started a little bit late. But I beg your pardon, sorry for the inconvenience. We're starting now with a session on renewable energy. Well, this is the first session of talking about renewable energy. We will have another one tomorrow morning, but this is about the general aspects. We will try to analyze the full range of renewable energy supplies available to modern economies worldwide. Yes, it is widely recognized that these are necessary for sustainability, security, and standard of living. The renewable energy systems will include powerful solar radiation, which is sunshine, wind, biomass, which are plant crops, rivers, which is hydropower, and ocean waves, tides, geothermal heat, and other such continuing resources. Well, all of these systems are included within the following general definition, which is included in the first slide. It's renewable energy is energy obtained from naturally repetitive and persistent flows of energy occurring in the local environment. An obvious example is solar, which is with sunshine. Solar energy that persists and repeats day after day, but is obviously not constant but variable. Similarly, plants have an annual growing season which stores energy from sunshine in the structure that is released in combustion and metabolism. With a renewable energy resource, the energy is already passing through the environment as a current or flow, irrespective of there being a device to intercept and harness this power. The phrase local environment refers to the location of such a device to intercept the flow. The natural energy flows that are commonly harnessed for energy purposes are more or less indicated here in this presentation. Such energy may also be referred to as green energy or sustainable energy. In contrast, we should say that non-renewable energy is energy obtained from static stores of energy that remain underground unless released by human interaction. Examples of those are nuclear fuels and the fossil fuels of coal, oil, and natural gas. These sources, the energy is initially an isolated energy potential, and external action is required to initiate the supply of energy for practical purposes. To avoid using the ungainly word non-renewable, such energy supplies can be called finite supplies or brown energy. It is also possible to include energy from society's wastes in the definition of renewables, since in practice they are unstoppable. But are they natural? Well, such finer points of discussion, we will have to see it later. For renewable energy, the scale of practical application ranges from tens to many millions of watts, and the totality is a global resource. However, for each application, 5 questions should be asked. First, well, we should consider how much energy is available in the immediate environment and what are the resources. Then we should ask ourselves what technologies can harness these resources, and can the energy be used efficiently? What is the end use? What is the environmental impact of the technology, including its implications for climate change? And what is the cost effectiveness of the energy supply as compared with other supplies? Well, in fact, the first are technical questions considered, yes, but then the last two, both issues on planning, social responsibility, sustainable development, and global impact. And well, that is maybe out of this presentation, but they should be considered. Well, the evaluation of cost effectiveness depends significantly upon the following factors. Well, first is appreciating the distinctive scientific principles of renewable energy. The efficiency, second, the efficiency of each stage of the energy supply in terms of both minimizing losses and maximizing economic and social benefits. Considering externalities and social costs, considering both costs and benefits over the lifetime of a project, which may be over 30 years. Well, now we're going to start with energy and sustainable development. Well, the first principle on major issues. Well, say a quote that we'll talk about afterwards. First, the principle on major issues of sustainable development. Sustainable development may be broadly defined as living, producing, and consuming in a manner that meets the needs of the present without compromising the ability of future generations to meet their own needs. It has become one of the key guiding principles for policy in the 21st century. The principle is affirmed worldwide by politicians, industrialists, environmentalists, economists, and theologians as they seek international, national, and local cooperation. However, reaching specific agreed policies and actions is providing much harder. Now, in the international context, the word development refers to improvement in quality of life, including improving standards of living in less developed countries. The aim of sustainable development is to achieve this aim while safeguarding the ecological processes upon which life depends. Locally, progressive businesses seek a positive triple bottom line. That is to say, a positive contribution to the economic, social, and environmental well-being of the community in which they operate. The concept of sustainable development first reached global importance in the seminal report of the United Nations World Commission on Environment and Development in 1987. Since then, this theme has percolated slowly and erratically into most national economies. The need is to recognize the scale and unevenness of economic development and population growth, which place unprecedented pressures on our planet's land, waters, and other natural resources. Some of these pressures are severe enough to be threatened, in fact, to threaten the very survival of some regional populations, and in the longer term to lead to disruptive global change. The way people live, especially regarding production and consumption, will have to adapt due to ecological and economic pressures. Nevertheless, the economic and social pain of such changes can be eased by foresight, planning, and community will. Energy resources exemplify these issues. Reliable energy supply is essential in all economies for lighting, heating, communications, computers, industrial equipment, transport, etc. Purchases of energy account for 5 to 10% of gross national product in developed economies. However, in some developing countries, fossil fuel imports, that is coal, oil and gas, may cost over half the value of total exports. Such economies are unsustainable and an economic challenge for sustainable development. World energy use increased more than tenfold during the 20th century, predominantly from fossil fuels and with the addition of electricity from nuclear power. In the 21st century, further increases in world energy consumption may be expected, largely due to rising industrialization and demand in previously less developed countries, aggravated by gross inefficiencies in all countries. Whatever the energy source, there is an overriding need for efficient transformation, distribution, and use of energy. Fossil fuels are not being newly formed at any significant rate, and thus current stocks are ultimately finite. The location and amount of such stocks depend on the latest surveys. Clearly the dominant fossil fuel by mass is coal. The reserve lifetime of a resource may be defined as the known accessible amount divided by the rate of present use. By this definition, the lifetime of oil and gas resources is usually only a few decades, whereas the lifetime for coal is a few centuries. Economics predicts that as the lifetime of a fuel reserve shortens, so the fuel price increases. Subsequently, therefore, demand falls and previously more expensive sources and alternatives enter the market. This process tends to make the original source last longer than an immediate calculation should indicate. In practice, many other factors are involved, especially government policy and international relations. Nevertheless, the basic geological fact remains. Fossil fuel reserves are limited, and so the current patterns of energy consumption and growth are not sustainable in the longer term. Moreover, the emissions from fossil fuel use, and indeed nuclear power, increasingly determine another fundamental limitation on the continued issue. These emissions bring substances derived from underground materials, for example, carbon dioxide, into the Earth's atmosphere and oceans that were not present before. In particular, emissions of carbon dioxide, CO2, from the combustion of fossil fuels have significantly raised the concentration of CO2 or carbon dioxide in the global atmosphere. Authoritative scientific opinion is in agreement that if this continues, the greenhouse effect will be enhanced and so lead to significant climate change within a century or sooner, which could have a major adverse impact upon food production, water supply, and society. Well, for example, to increase floods and storms. Well, you never know that that's a potential future. Sadly, well, concrete action is quite slow, not least owing the reluctance of governments in industrialized countries to disturb the lifestyle of the voters. However, potential climate change and related sustainability issues is now established as one of the major drivers of energy policy. Well, in contrast to fossil and nuclear fuels, renewable energy, RE, supplying operation does not add to elements in the atmosphere and hydrosphere. In particular, there is no additional input to greenhouse gases. Although there are normally such emissions from the manufacture of all types of energy equipment, these are always considerably less per unit of energy generated than emitted over the lifetime of fossil fuel plant. Therefore, both nuclear power and renewables significantly reduce the greenhouse gases emissions if replacing fossil fuels. Moreover, since renewable energy supplies are obtained from ongoing flows of energy in the natural environment, all renewable energy sources should be sustainable. Nevertheless, great care is needed to consider actual situations, as noted in the following quotation that I included here in the presentation from the IPCC, the Intergovernmental Panel on Climate Change. And this quoting says, for renewable energy resource to be sustainable, it must be inexhaustible and not damage the delivery of environmental goods and services, including the climate system. For example, to be sustainable, biofuel production should not increase net carbon dioxide emissions, should not adversely affect food security, nor require excessive use of water and chemicals, nor threaten biodiversity. Should be sustainable. Energy must also be economically affordable over the long term. It must meet societal needs and be compatible with social norms now and in the future. Indeed, as, as use of renewable energy technologies accelerates, a balance will have to be struck among the several dimensions of sustainable development. It is important to assess the entire life cycle of each energy source to ensure that all the dimensions of sustainability are met. Well, in analyzing harm and benefit, well, to say that the full external cost of obtaining materials and fuels and of paying for damage from emissions should be internalized in costs. Doing so takes into account, first, the finite nature of fossil and nuclear fuel materials, and second, the harm of emissions. Well, could include the third, ecological sustainability. Well, such fundamental analysis usually conclude that combining renewable energy with the efficient use of energy is more cost effective than the traditional use of fossil and nuclear fuels, which are unsustainable in the longer term. In short, renewable energy supplies are much more compatible with sustainable development than are fossil and nuclear fuels in regard to both resource limitations and environmental impacts. Consequently, almost all national energy plans include 4 vital factors for improving or maintaining benefit from energy. First, increased harnessing of renewable supplies. Second, increased energy of supply and end use. Third, reduction in pollution. And fourth, a consideration of employment security and lifestyle. Well, regarding energy security, well, nations and indeed individuals need secure energy supplies. They need to know that sufficient and appropriate energy will reach them in the future. Being in control of independent and assured supplies is therefore important. Renewables will offer this so long as the technologies function and are affordable. Both things have to be implemented. They should function and be affordable. Well, there are many numerical models for sustainability. Well, we're not going to consider them here, but well, there are many studies on that issue. We should consider the global resources. Well, with the most energy efficient modern equipment, buildings and transportation are justifiable target for energy use in a modern society could be 2 kilowatts per person. That means approximately the current global average usage, yet with a far higher standard of living. Well, is this possible, even in principle, from renewable energy? That's a great question. Each square meter in the Earth's habitable surface is crossed by or accessible to an average energy flux of about 500 watts. Well, this includes solar, wind, or other renewable energy forms in overall estimate. If this flux is harnessed at just 4% efficiency, 2 kilowatts of power can be drawn from an area of 10 meter per 10 meter. That's 100 square meters, obviously. Assuming suitable methods. Some urban areas of residential towns have population densities of about, well, I should say 500 people per kilometer, per square kilometer. At 2 kilowatts per person, the total energy demand of 1,000 kilowatt per square kilometer could be obtained in this way by using just 5% of the local land area for energy production, thus allowing for the technical potential of renewable energy being less than the theoretical potential. Thus, renewable energy supplies may, in principle, provide satisfactory standard of living worldwide, but only if methods exist to extract, use, and store the energy satisfactorily and at realistic costs. Well, we will try to consider all these considerations. Now for the energy resources fundamentals. Well, first, definitions of renewable energy have already been given, and fossil and nuclear energy. Well, we may have now a comparison of renewable and conventional energy systems. There are 5 ultimate primary sources of useful energy, which are, as it says in the slide, the sun, the motion and gravitational potential of the moon, the sun, and the earth, geothermal energy from cooling, chemical reactions, and natural radioactive decay, nuclear reactions on the earth, chemical reactions from mineral sources. Sorry. Sorry. Renewable energy derives continuously from the first 3 sources mentioned. That is the sun, the motion, gravitational potential, and geothermal energy. Well, this is expressed in this contrast between renewable and finite energy supplies. Well, now we're going to see what I promised before, the general comparison. As you can see in the slide, well, we have some examples of renewable energy supplies, which are considered the green ones, and then the conventional energy supplies, which are called also the brown ones. Some examples: wind, solar, biomass, and tidal are examples of renewable energy supplies, while coal, oil, gas, and radioactive ore are considered conventional energy supplies. Now, the sources, well, in the case of the renewable energy supplies, natural local environment, and in the case of conventional energy, is a concentrated stock. Well, the normal state of the renewable energies is a current of flow of energy and income, while conventional energy is a static store of energy, capital. Well, here we have the difference in intensities. Well, this could be studied in detail. This is, well, just one of the studies. There are many more. This is just an example. Well, renewable energies are considered infinite, while conventional energies are finite. So the cost at source for the renewable energies should be considered free, while in the case of conventional, it is increasingly expensive. Well, same, we should consider then the cost for the equipment, which is more currently more in the case of renewable energies. But if we consider the reduction of emissions, well, it may not be that clear. And then we can also see the variation and control. Well, in the case of renewable energies, it is fluctuating, best controlled by change of load using positive feed-forward control of complementary sources, while in the case of conventional energy supplies, is steady, best controlled by adjusting source with negative feedback control. The location for use in the case of renewable energies are site and society specific, while in the case of conventional, it is general and global use. The scale, it is small scale, often economic in the case of renewable energies, while it is increased scale often improves supply costs. Large scale frequently favored. That was meaning in the conventional fuels, energy supplies, which we are calling that. And then the skills in the case of renewable energy, interdisciplinary and varied, wide range of skills, importance of bioscience and agriculture. While in the case of conventional energy supplies, the skills were strong links with electrical and mechanical engineering and a narrow range of personal skills. Well, the context of renewable energies are well adapted to rural situations and decentralized industry, while in the case of conventional energy supplies, the context is scale favors urban centralized industry. Well, in the case of high frequency dependence, in the case of renewable energies, self-sufficient systems encourage. Well, in the case of conventional energy, this dependence, well, concerning dependence, systems are dependent upon outside inputs. Considering safety in the case of renewable, local hazards are possible in operation, usually safe when out of action. In the case of conventional energy supplies, well, they may be shielded and enclosed to lessen great potential dangers, most dangerous when faulty. So if not faulty, then most probably not dangerous. If we consider pollution and environmental damage, in the case of renewable energy, we have to say that usually little environmental harm, especially at moderate scale, hazards from excessive wood burning, soil erosion from excessive biofuel use, large hydro reservoirs disrupted. In the case of conventional energy supplies, well, regarding pollution and environmental damage. Well, environmental pollution is common, especially of air and water. And we have to consider permanent damage, which is common from mining and radioactive elements entering water table, deforestation and ecological sterilization from excessive air pollution, greenhouse gas emissions causing climate change. Well, that may be an opinion we should consider that, at least for now. Now, differences in aesthetics and visual impact. Local perturbations may be serious in the case of renewable energies, but are usually acceptable if locally perceived. Well, in the case of conventional energy supplies, they're usually utilitarian with centralization and economy of large scale. Well, just a second. Now, you should consider environmental energy. Well, then the flows of energy passing continuously as renewable energy through the earth is shown in the slide. For instance, a total solar flux absorbed at sea level, well, could be 1.2 to the 17th potence in watts. Thus, the solar flux reaching the Earth's surface is about 20 megawatts per person. 20 megawatts is the power of 10 very large diesel electric generators, enough to supply all the energy needs of a town of about 50,000 people, which is quite a lot, I consider. Maximum solar flux density irradiance perpendicular to the solar beam is about 1 kilowatt per square meter. A very useful and easy number to remember. In general terms, a human being is able to intercept such an energy flux without harm, but an increase begins to cause stress and difficulty. Interestingly, power flux densities from wind, waters or waves are more than 1 kilowatt per square meter, also begin to cause physical difficulty to an adult. Well, in the slide, we can see, well, natural energy currents on the Earth, showing renewable energy systems. Note the great range of energy flux and the dominance of solar radiation and heat. Unit terawatt, as it is indicated in the slide. Well, however, global data that we have more or less exposed have little value for practical engineering applications, since particular sites can have remarkably different environments and possibilities of harnessing renewable energy. Obviously, flat regions such as, for example, Denmark, have little opportunity for hydropower, but may have wind power. Yet neighboring regions, for example, Norway, may have a vast hydro potential. Tropical rainforests may have biomass energy resources, but deserts at the same latitude have none. Moreover, forests must not be destroyed, which would make more deserts. Thus, practical renewable energy systems have to be matched to particular local environment energy flows occurring in a particular region. Well, all energy systems must be visualized as a series of pipes or circuits through which the energy currents are channeled and transformed to become useful and domestic, industrial and agricultural circumstances. Well, which Well, let's see. We have to note another thing that how the total energy in use is less than the primary supply due to losses in the transformation processes, notably the generation of electricity from fossil fuels. Now, regarding energy planning, we have these pictures of renewable. We'll see that later. Now, energy planning, certain common principles apply for designing and assessing energy supply and use. Whether we are considering energy supply at the level of a nation, a city, or a household. First instance, the complete energy systems must be analyzed, and supply should not be considered separately from end use. Unfortunately, precise needs for energy are too frequently forgotten, and supplies are not well matched to end use. Energy losses and economic operation therefore frequently result. For instance, if a dominant domestic energy requirement is heat for warmth or hot water, it is irresponsible to generate great quality electricity from a fuel, waste the majority of the energy as thermal emission from the boiler and turbine, distribute the electricity with losses, and then dissipate the delivered electricity as heat, a total loss of about 75%. Well, sadly, such inefficiency, disregard for resources, and unnecessary associated pollution often occur. Heating will be more efficient and cost-effective from direct heat production with local distribution. Even better is to combine electricity generation with the heat production using CHP, which is a combined heat and power electricity. Well, let's go on. System efficiency calculations can be most revealing and can pinpoint unnecessary losses. Here we define efficiency at the ratio of the useful energy output from a process to the total energy input to that process. Consider electric lighting produced from conventional thermally generated mains, electricity and lamps. Successive energy efficiencies will be electricity generation at about 30%, distribution at 90%, about 90%, and incandescent lighting, which is energy in visible radiation, usually with a light shade, is 4 to 5%. The total efficiency is about 1 to 1.5%. Contrast this with the cogeneration of useful heat and electricity, which has an energy efficiency of about 85% and a distribution of about 90%. And lighting in modern low consumption compact fluorescent CFL light of about 22%, or light emitting diode LED light of about 80%. The total efficiency is now about 17 to 60%, and energy efficiency improvement by factors of 10 40. So it was kind of a connection question. No questions? No questions. Okay. Just a second. And now we're back again where we were. Well, where were we? The total life cycle cost of the more efficient system will be much less than for the conventional system, despite higher per unit capital costs, because first, less generating capacity and fuel are needed, and second, equipment, especially lamps, last longer. Now, energy management is always important to improve overall energy and reduce economic losses. No energy supply is free, and renewable supplies are capital intensive. Thus, there is no excuse for wasting energy of any form unnecessarily. Efficiency with finite fuels reduces pollution. Efficiency with renewables reduces capital costs. Well, now we go for the scientific principles of renewable energy. Well, should say, well, for the dynamic characteristics, the end use requirements for energy vary with time. For example, electricity demand on our power network often peaks in the mornings and evenings, and it reaches a minimum through the night. If power is provided from a finite source, such as oil, the input may be adjusted in response to demand. Unused energy is not wasted, but remains with the source fuel. However, with renewable energy systems, not only does end use vary uncontrollably with time, but so too does the natural supply in the environment. Well, let's see now some in the table, some intensity and frequency properties of renewable sources. This is well analyzed there. We're not going to read all the things. Well, now the quality of supply. Well, we should define quality as the proportion of an energy source that can be converted to mechanical work. Thus, electricity has high quality because when consumed in an electric motor, more than 90% of the input energy may be converted to mechanical work. Say, to lift a weight, the heat losses are therefore small, less than 10%. The quality of nuclear, fossil or biomass fuel in a single stage thermal power station is moderate because only about 33% of the caloric value of the fuel is transformed into mechanical work, and about 67% is lost as heat to the environment. Well, if the fuel is used in a combined cycle power station, that is methane gas turbine stage followed by steam turbine. The quality is increased to about 50%. It is possible to analyze such factors in terms of the thermodynamic variable exergy, defined as the theoretical maximum amount of work obtainable at a particular environmental temperature from an energy source. Well, renewable energy supply systems are divided into three broad classes. The first would be mechanical supplies, such as hydro, wind, wave, tidal power. The mechanical source of power is usually transformed into electricity at high efficiency. The proportion of power in the environment extracted by the devices is determined by the operational limits of the process, linked to the variability of the source. Well, the proportions are typically for wind more or less 35%, for hydro 80%, for wave about 30%, and tidal range about 60%. Well, these proportions relate to the capacity factor and load hours of the devices. That we will see those factors a bit later in this presentation. Heat supplies, such as biomass combustion. Well, these sources provide heat at high efficiency. However, the maximum proportion of heat energy extractable as mechanical work, and hence electricity, is given by the second law of thermodynamics and the Carnot theorem, which, well, assumes reversible, infinitely long transformations. In practice, maximum mechanical power produced in a dynamic process is about half that predicted by the Carnot criteria. For thermal boiler heat engines and internal combustion engines, the maximum possible in practical terms is a quality of about 35%. And third would be photon processes, such as photosynthesis and photochemistry and photovoltaic conversion. For example, solar photons of a single frequency may be transformed into mechanical work with high efficiency using a matched solar cell. In practice, the broad band of frequencies in the solar spectrum makes matching difficult, and photon conversion efficiencies of about 25% are considered quite good. Well, now we have to compare dispersed versus centralized energy. Pronounced difference between renewable and finite energy supplies is the energy flux density at the initial transformation. Renewable energy commonly arrives with a flux energy of about 1 kilowatt per square meter. For example, solar beam irradiance energy in the wind at 10 meters per second, whereas finite centralized sources have energy flux densities that are orders of magnitude greater. For instance, boiler tubes in gas furnaces easily transfer 100 kilowatts per square meter. And in a nuclear reactor, the first wall heat exchanger must transmit several megawatts per square meter. At end use after distribution, however, supplies from finite sources must be greatly reduced in flux density. Thus, apart from major exceptions such as metal refining, end-use loads and for both renewable and finite supplies similar. In general, finite energy is most easily produced centrally and is expensive to distribute. Renewable energy is most easily produced in dispersed locations and is expensive to concentrate. Well, thus, renewable energy technologies encourage dispersed and distributed energy systems. These are installed by companies and utilities, for example, wind farms, a tidal current plant, sugarcane mills, and also a smaller scale, microgeneration of heat and electricity by individuals, small businesses, and communities as alternatives or supplements to traditional centralized quick connected power. Examples of microgeneration include photovoltaic arrays, combining heat and power on industrial sites, and biogas on farms. A worldwide benefit, especially in developing countries, is that modern renewable energy technologies enable remote communities to enjoy benefits and services. For example, we should say lighting and telecommunications, previously confined to urban population. When renewables installations are of a large scale of about 500 megawatts or more, for example, offshore wind farms, hydro generation, biomass thermal plants, then special transportation and electricity high voltage transmission lines are needed. Often, these delivery systems feed the energy to urban complexes. The complex systems, renewable energy supplies are intimately linked to the natural environment, which is not the preserve of just one academic discipline, such as physics or electrical engineering. Frequently, it is necessary to cross disciplinary boundaries from apparatus, say, plant physiology to electronic control engineering. For example, modern sugarcane industries produce not only sugar, but also liquid fuel, for example, ethanol. Ethanol. The complete process in a rural society requires input from agricultural science and sociology, as well as chemical, mechanical, and electrical engineering. Well, if we are consider the situation dependence, no single renewable energy system is universally applicable, since the ability of the local environment to supply the energy and the suitability of society to accept the energy vary greatly. It is as necessary to prospect the environment for renewable energy as it is to prospect geological formations for oil. Nevertheless, appraising the potential of renewables resources is usually much easier. usually, well, much easier and also cheaper than prospecting for oil. It is also necessary to conduct energy service of the domestic, agricultural, and industrial needs of the local community. Well, particular end-use needs and local renewable energy supplies may then be matched, subject to economic and environmental constraints. In this respect, renewable energy is similar to agriculture. Particular environments and soils are suitable for some crops and not for others. And the market pool for selling the produce will depend upon particular needs. Thus, solar energy systems in southern Italy, for example, should be quite different from those in Belgium, for example, or indeed in northern Italy. Corn alcohol fuels may be suitable for farmers in Missouri, but not in New England. The consequence is that planning for optimum renewable supply and use tends to apply to regions of distance scale of about 250 kilometers, but not 2,500 kilometers. Because of greater distances, supply options are likely to change. Unfortunately, large urban and industrialized societies have built up in ways that are not well suited to such flexibility and variation for optimizing renewables supply and demand. Now we're going to talk about technical implications. Well, technical implications, what should we say about that? Well, the first step is a rapid appraisal of which renewables sources are in sufficient quantities to warrant more detailed monitoring. The order of magnitude formula, well, usually given by technology uses for the purpose, well, is due to seasonal variations in most renewables options. Well, the resource has to be monitored for at least a full year at the site in question, because not every site has the same characteristics. For large-scale projects, for example, if it is hydro more than 100 megawatts, a decade or more data may be needed. Ongoing analysis must ensure that useful data are being recorded, particularly with respect to dynamic characteristics of the energy systems plan. Meteorological data are always important, but unfortunately, the sites of official stations are often different from the energy generating sites, and the methods of recording and analysis are not ideal for energy prospecting. However, an important use of the long-term data from official monitoring stations is as a base for comparison with local site variations. Thus, wind velocity may be monitored for several months at a prospective generating site and compared with data from the nearest official base station. While extrapolation using many years of base station data may then be possible. Nevertheless, long-term variations in weather occur, with the debate continuing about how much is due to human-induced climate change? Well, data unrelated to normal meteorological measurements may be difficult to obtain. In particular, flows of biomass and waste materials will often not have been previously assessed and will not have been considered for energy generation. In general, prospecting of supplies of renewable energy requires specialized methods and equivalent equivalent to, sorry, I just lost myself. Equivalent to significant resources of finance and manpower. Well, fortunately, the links with meteorology, agriculture, and marine science give rise to a considerable amount of price information. Well, since no energy supply is cheap or occurs without some form of environmental disruption, it is essential to use energy efficiently, often called energy conservation. With electrical systems, the end use requirement is called the local or demand. The size and dynamic characteristics of the generation need to be matched to the load requirements. As explained before, it will be explained afterwards in energy conservation. Money spent on energy conservation and improvements in energy use efficiently usually give better long-term benefits than money spent on increasing generation and supply capacity. The largest energy requirements are usually for heat and transport. Both uses are associated with energy storage capacity in thermal mass, batteries, or fuel tanks, and the inclusion of these components in energy system design can greatly improve overall efficiency. So just a second. Well, after quantification and analysis of the separate dynamic characteristics of end-use demands and environmental supply options, after quantification and analysis of the separate dynamic characteristics of end-use demands and environmental supply options, the total demand and supply are joined as an energy system. Well, the principles apply in some measure to supplies of heat and fuel, but are immediately applicable to matching electricity supply and demand. I'm going to see this supply and demand. Let's see. Well, here we can see in the symbols. The symbols. This symbol, sorry. That means energy current source, while this symbol here should be a control device. Well, here we can see the energy flow. Okay, these are the symbols mainly. Well, now, first A corresponds to maximum energy flow for minimum size of the box. All system requires low resistance to flow at D, E, and F. Okay. B, negative feedback control for a system with finite sources allows fuel to be saved as load decreases. C, negative feedback for a system with purely renewable input spills energy beyond that required by the load. D, positive feed-forward load management control of the supply, separating high priority and low priority loads, so that total load at E may be matched to the available supply at D at all times. Now let's see. This one with the same symbols. This is the continuation of previous slide. Here we can see the energy, it's E, yes. The energy storage allows dynamic characteristics of end use to be decoupled from the supply characteristics. And F, a large grid system, it can incorporate both feedback to adjust the supply to the demand and the feed forward to switch on low priority loads only when the supply is adequate. So now let's talk about efficiency. Efficiency, well, we could say that as efficiency, a common question from the public could be, how efficient are renewable energy devices, for instance, wind turbines and solar panels? Well, however, what appears to be a simple question, it cannot be answered so easily. Neither is it easy to answer questions like, how efficient is that motor car? But how efficient is that athlete? Or how efficient is that electric clock? Questions like this are never simple, especially as the questioner often means, is that device cost effective? Well, some answers questions could be not given. Well, does efficiency matter? Well, it seems obvious at first sight that technological devices should be efficient. However, this word means different things to different people about different technologies. As the examples, well, we have seen illustrate for energy generation devices. For a refrigerator, for example, the concept of efficiency includes considering if the volume is sufficient for needs, if the door opens and closes easily, and if the electricity consumption is acceptable. Well, in practice, many factors are relevant. Decisions are and should be made by comparing one device with another until a final option is selected. Nevertheless, we still tend to say that we have chosen the most efficient refrigerator. Well, technical efficiency of an energy device usually means the useful energy supplied as a fraction of the input energy. By this definition, the best efficiencies at various common devices are as shown in the slide that we have here. Well, we see the power stations, well, cars, cyclists while racing, regular cyclists over a year, electricity generator, this bicycle, sorry, incandescent electric light. What else? Light emitting diode. Well, it is clear that first, efficiency has to be defined very carefully for each question, and secondly, there is an important devices may have small efficiencies, but this does not prevent their use. Moreover, the input energy usually does not include the energy to sequester the fuel for food. If this is included, efficiencies may become much less. For renewable energy devices, we start by using a simple definition. The efficiency being useful energy supplied as a fraction of the input energy. Thus, hydroelectric power station electricity, which is electricity to grid, initial potential energy of piped water onto the turbine board is about 90%. A wind turbine in moderate wind, well, it's about 45%. Solar water heater at midday, clear sky, with tank temperature initially cold, is about 60%. Solar photovoltaic panel, midday, clear sky, is about 17%. Wood burning stove and in-room flue pipe is about 85%. Biogas burner is 90%, about 90%. And biomass thermal power station is about 30%. But these are these values of efficiency of great significance, since the inputs for renewable energy devices usually arrive without cost to the local environment as rain, wind, sunshine, and waste. If we pay for the input, for example, fossil fuel, then device efficiently is very important. But if the inputs are free, it is more important to assess the actual production of particular devices at specified sites. Moreover, the environmental inputs are very variable, so the inputs are best averaged over time, usually a year. Well, we establish parameters that allow the annual production of a device to be assessed at particular sites, for which the term capacity factor or full load hours is used. Now, we can see in the slide the definitions of capacity factor. Normally specified period is 1 year, 365 days. So that means for a 24 hours day, that means 8,760 hours per year. So that changes the factor into the annual capacity factor, and also the full load hours. Hence, annual capacity factor are full load hours per 365 hours, as you can see in the slide. Well, the value of these parameters for a device depends both upon its own efficiency and upon the climate at the site. Therefore, for instance, we have some examples that, well, more or less you can see them. let's see, then the capacity, well, factors that are most, capacity factors are most frequently discussed in the case of electrical power generation, but concept may be applied more widely. Note that solar devices can only capture sunshine in daytime. So if year includes nighttime, then the capacity factor is at most 50%, even for a perfect device in an average day of 12 hours, not 24. Well, note that, values, you can see in the slide, Z and TF, which are annual capacity factor and full load hours, are both independent of the capacity of the device. So if the values for a particular site and technological are considered small, increased output may only be obtained by increasing the capacity of the installation. In addition, since the comparison is with the maximum capacity of the device itself, these factors do not in themselves give information about efficiency. They do, however, allow different devices of the same technology to be compared, either by on the same site or by site with similar devices. Obviously, manufacturers and device owners try to maximize the factors with values that approach a theoretical maximum, but there are usually limitations owing to the particular technology and the site and applications. Well, now, the resource potential. We talk about, yes, the factors influencing capacity factors. You can see there the resource potential of a renewable device.
Invece singing.
There is something here disturbing. No, not anymore. Well, the resource potential of a renewable device is the energy that it can supply per year. The resource may be estimated at any geographic scale, from a household to the whole world. There are two common measures of resource potential in a geographical area. First, we have theoretical potential derived from natural and climatic parameters. And two, we have the technical potential, which is the amount of renewable energy output obtainable by the full implementation of demonstrated technologies or practices in the specified region. No explicit reference is made to cost, institutional policies, or other man-made barriers that may limit take-up of the technology. From the technical potential, more practical estimates can be made, allowing for other constraints, for example, avoiding sites of scientific or ecological value, prioritizing biomass for good use ahead of its use for energy, applying cost limits, etc. Now, using energy efficiently, what can we say about this? Well, first, sorry, we're going to do something. Here we have an indicative diagram of energy flows from source to end-use service. Let's see. Well, improved energy use and thus less energy demand increases opportunity for renewable energy systems. Well, this presents opportunities to reduce the use of fossil fuels and shift to clean, sustainable systems. Double opportunity for greenhouse gas reduction. Well, energy supply is costly, requiring infrastructure, for example, transportation, electricity grids, maintenance, and equipment to convert the primary energy to a usable form. Therefore, reducing energy demand without loss of benefit reduces ongoing cost for the customer. For example, the capacity and hence the cost of photovoltaic panels and ancillary equipment for daytime internal lighting depend on the control of the required illumination and the efficiency of the light. Better control and efficiency require less capacity and hence less PV capital cost. For the energy supplier, less demand means less capital expenditure on plant capacity and the opportunity to integrate renewable energy sources. However, the supplier's income for consumer bills reduces unless per unit charges are increases. So governmental regulation is needed for a fair and energy efficient system. Well, one general principle is that we do not require energy as such, but the energy services provided, such as lighting, heating, communication, and transport. These services are what are called end uses. Well, in supplying energy for service, the primary energy is, for example, the chemical energy content of fuel or the energy from solar radiation onto a photovoltaic device. There are many conversion and supply steps along the way. The whole process has many definitions, but it could be energy output per energy input. That's the main consideration. Now here we can see the diagram. That's an indicative diagram of energy flows from source to end use service. Note how different routes depend on the technologies concerned. For instance, from wind to lighting in the diagram may require 2 steps, yet from nuclear fuel to lighting requires 4 steps. At each step, there is a loss of energy since no transformation is 100%. Now let's see energy services. Which are the service? It is the service function from energy that matters, not the energy itself, as we mentioned before. We need heating, lighting, delivery of goods, movement of people, communication of information, and many other such benefits. Well, the thermodynamic limitations of thermal conversion by heat engines are particularly important, as with vehicle combustion engines and with power station turbines for electricity generation. Carnot theory explains that only a fraction of input heat energy can be transformed into mechanical work output, with the remainder emitted to the environment as lower temperature heat. The practical consequence is that whatever heat is converted to work, as in engines and turbines, the mechanical efficiency is at best about 45%. Well, we could say practically often it is about 35% for coal nuclear power stations, and commonly less biomass combustion and geothermal power stations, most vehicle engines. The largest energy output is therefore not useful work, for example, as shaft power for electricity generators, but the waste heat in the exhaust or cooling tower. Of course, if the output heat can itself be used beneficially, it is no longer waste, and the overall efficiency should be improved considerably. Now we're going to make a kind of specifications for transport. Let's see, specifications for transport. Now, so I have in my notes some examples of buildings, but we have to check this. This transport issue, as this is the what this is what this TrainMoS II is mostly about. Well, let's see if I can find it in my notes. Okay. Okay, first we could say a kind of background. Well, transport is generally considered as the movement of goods and people by powered vehicles. Thus, despite their importance, walking and cycling tend to be neglected by transport planners and statisticians. Powered vehicles account for between 20% and 30% of primary energy use within most economies. However, within official statistics, such data often does not include international journeys and international trade by air and sea. The movements of people and of goods and commodities, including fossil fuels, are major components of the global economy. Then, well, considering vehicles, the motive power mechanisms for common modes of land transport are following that I'm going to mention. First, metabolism, in case walking, running, cycling, animal power, wind, sailing boats, for example, electric motor grid connected, electric trains and trams, electric motor from onboard rechargeable battery, or fuel cell electric cars, lightweight vans or lorries, cycles, and hybrid vehicles, internal combustion engines with liquid or liquefied fuel. Don't know if that sounds familiar to you because of all the time we've been talking about liquefied natural gas. And internal combustion with gaseous fuel, spark ignition engine for road vehicles with tanks of compressed methane and hydrogen. Well, the efficiency of the various engines is in two classes, either electric or thermal combustion. Well, grid-connected electric motors, as in trains and trams, convert about 90% of the electric power into motive power. The overall efficiency depends on how electricity is generated and transmitted. Most battery-powered electric motors are also about 90% efficient, electric power to shaft power, but the battery charging and discharging processes in practice between 50% and 80% efficient, depending especially on the age and use of the battery. The overall system's efficiency of electric machines depends on the efficiency of the electricity generation at source and on the grid transmission efficiency. Practical spark ignition engines are usually about 35% efficient from fuel to shaft power, with the remaining energy being emitted heat of no value in a vehicle other than comfort heating, with diesel engines slightly better. The overall system's efficiency of thermal engines depends on the energy used by the supply system in providing the fuel. For example, refining petroleum and transporting it to the browser. This is normally unknown to the consumer. The gearbox, the transmission, and losses to air and road friction lead to further energy losses in real vehicles, so that the well-to-wheels efficiency of vehicles with such engines is usually under 10%. Well, do we have an unsustainable transport system? Well, several components of the present transport systems make them problematic in environmental, economic, and social terms. Well, diminishing fossil oil reserves. The present system is almost entirely fueled by petroleum products, which is something that we are trying to reduce. Global atmospheric impacts. Well, there are many emissions that we're talking about in this module so long. Local air quality impacts. Urban smog caused largely by vehicle exhaust is health hazard, as lead was from leaded petrol. Noise, especially from motorways and freeways and in cities. Well, we should also consider fatalities from road accidents. Well, also inadequate air mobility in developing countries. Poor infrastructure prevents many people from bringing their produce to market and from accessing what facilities are for healthcare and education. Well, renewable energies, particularly biofuels and also with electric vehicles, contribute to mitigating all these things, particularly first and second, the using fuel, the fossil oil reserves, and the global atmospheric impacts. Well, the other issues are reduced by improving resources and better control technology and public responsibility. Well, I think this may be over for now, and thank you very much for your attention. And we'll continue tomorrow in the morning, 9:30. Thank you very much. Bye bye.